3/4 of the class will be here. So, and I got confused. So April 20th, Thursday, I will have to be in class. Because when you guys can be here. Alright. We're going to talk about this other approach to designing these controllers. The idea is that we define a penalty function. Which is, you'll see different people use different forms. You generally can have an endpoint. I'll show you an example of one of these input penalties. It's kind of an interesting result. And then you have this path penalty. So from some time to final time, we'll usually write it. Some sort of what is called path penalty. And this is the one we're mostly interested in because that's the one that's going to be part of the regulator. All right, so we went through a lot of math. So take this. How do I minimize? It's usually I want to minimize this. And how do you minimize? Take derivatives of things. A little bit messier here because this is a nice simple function. In fact, really, it's classic way of doing this is we find the not the derivatives of the differential, and we minimize the differential. Right? Anyway, we have this thing we want to minimize. A lot of math. All right, which I don't expect you to be able to derive these things. Don't worry about that. And the result is what we call a Riccati equation. Right? If we solve this Riccati equation, we can define the gains that will solve this minimization problem. Okay? So you guys don't need to worry about that step. Right? You do need to see how do I do this part, and then finally how do I use this Riccati equation. Okay? And we'll do it for both controllers. We've done some examples on, so I can say, hey, I want the position to be a certain amount of penalty, velocity, voltage, whatever. I can state weights of these things. We can also make these for observers. We'll do this next week. And that observer using your Riccati equation just as a counting function. Now we do some examples today. We'll start off simple. 1D. Here's our state equation. Can't get much simpler than that. And we'll define the penalty here. Interval, initial final time of x squared plus u squared. U by scale of 1 and f by 2. And if you look at the matrices of this, it's a scalar, but really think of a scalar as 1 by 1 matrix. It's A matrix, this will be 1/2. B matrix is 1. My Q matrix is a 2. And my R matrix is a 1. Okay. All right. So let's look at the Riccati equation.
Is there no endpoint penalty in this?
I'm going to do this record, so I'm going to ignore the input penalty. So, for a really long time, this guy goes on to infinity. This becomes a regulator. What your regulator means is keep the status quo. Right, that's the only way to track those kind of problems. I'll do another problem where we'll do that, see the art. I didn't trust it. All right. Well, let's look at the Riccati equation. And, all right, I used K here. I'll change it. I think we used M. I'll try to change everything to M. That's the Riccati equation in the differential form, nonlinear differential equation. If we're looking at solely a regulator, this thing's constant. So the derivative disappears. Okay. Any qualms about that? It's a steady state. All right, well, let's put in numbers. What's that? 4. Doing my sums here. That's m plus m squared minus 2. Or m squared plus m minus 2 equals 0. Okay. Simple in this case. And of course you solve this with quadratic, and you'll have two values, 1 and minus 2. So, to do that, two values here. And next we're going to find the gains, K. And if you remember what we had last time, that was minus R inverse B transpose times our solution here. And you put in numbers. This is minus 1, 1, 1, minus 1, or 3 minus 1, 1, 2, minus 2, sorry, or 2. So 2 possible gains, minus 1 and 2. All right, now, here's our system. Do the block diagram. Our state equation is really pretty simple. Transfer functions are quite simple also. And this can either be a minus 1 or a 2. That form. You'll notice that I have a minus sign here. When I do the gain, then apply a plus sign there. Are they both valid? Both solve the Riccati equation. But what should we always check?
Stability.
Stability. So in this we check stability. One is a valid solution. Because it's from a quadratic, you can get a valid solution and you can get an invalid solution. Right? And that's the nature of quadratic. Right? It'll give you numbers that you don't need anything. So find out what I think it's the minus 1 is going to be the one that's stable. Okay. Question is, as simple as we can get. Yeah.
Sorry, how did you get your B equation with the synagogue? From the state equation you get B, right? Or is that just given?
D.
Yeah.
I gave this. I said what Q and R are. So these I gave. I defined those. So these are the things you need to define. And this system, really looking at how to solve the time equation. I said, well, we use these, this Q and this R. Notice the one that has to be non-zero is R. Because we have its inverse here. And its inverse here. Right? So that R must be positive definite. This is the one. Okay, but always have to have some sort of penalty or maybe really small, something I don't care about, but it needs to be non-zero. All right? Other questions on this? Try a little more complex one. Okay, 2 by 2. Second order. Okay, so here I have some mass with a force acting on it. That's it. Okay. So I have a regulator here that I might be trying to maintain status quo of this mass, even though there might be disturbances acting on it, whatever. I'm trying to keep it in place. You could think of this thing also, I'm trying to keep it at a certain position, or maybe I could even pose it as I want to keep it at a certain velocity. You know, in this case, I want to just keep it like this. What are the state equations for this? X1 would be what? Position. Better have position here. Why better have position? Because I'm trying to keep it in place. So you're repeating back what the position is. So this would be position. Okay. What would be your next state?
Velocity.
And the state equation is simply what?
X1 dot equals
X2 dot is what? X2 dot is acceleration. So if I have a force and a mass,
F over M.
it's simply solving Newton's laws. It'll be rainbow. Really simple system here. So no friction, no stiffness. And a force is going to accelerate the system. This is the same kind of problem I think of a spacecraft thing, right? Where if you're out in space, I put some thrust right here, it's going to cause acceleration of this potato thing. Nothing's going to stop it. Okay. State equation. I think we can write it down. What's the M matrix? And the B matrix? Okay. Well, let's look it up. Penalty. Publish it here. And again, I'll just look at the path here, keeping it steady state here. So it's going to be the form of some x transpose qx, u transpose ru, so I need to find q and r. Okay. What would I use for q? I want to keep it in place.
You 1 over whatever your tolerance level
Or it
is.
says, well, wait, keep it simple. 1, keep it massive, whatever. Yeah. Then we have range of colors and position.
Then the rest of zeros.
Certainly, usually if we have these diagrams, so those would be zeros. What about this one? Velocity. Well, if I didn't care how fast it went,
B0.
it'd be be 0. All right, so this is penalizing the motion, or the position, I should say. Right? And it is what? Positive semi-definite. That's okay for Q. It can be positive semi-definite. R cannot be. I'm going to say some equals or what that vectors. Okay with this?
Sorry, where did that be?
I have to have some positive definite value for an R. Then I'm just going to call some constant. We'll see what the effect of that was. So P is a positive number. All right? Let's look at the Riccati equation. In this case, and it will be in this form, we'll look at the algebraic form. Oops. So our M has, is of what order? It's going to be what? 2 by 2. Okay?
The minus before the first MA. Minus MA minus
MA minus M transpose
No,
A.
it's negative MA minus A transpose M.
yeah.
Wait, what do they do? Oh, the minus in the first one, I'm sorry, this one. Down. Is that right there? There you go, written down right now. So let's look at the second. M is of what order? There we go, 2 by 2. With 4 values. Minus sign here. Times your A matrix. Minus the transpose of the A matrix. Times plus R inverse is equal to P. B transpose 0, 1. We're in room. Q is 1, 0, 0, 0. All right. Put in equation. So I have 4 things to solve. How many equations do I have? I only have 2 here. Oh, one thing to note about M is it's going to be symmetric. So it says M12 is equal to M1.